line connected? What do you think? Can we show that? In fact, let's show something that's maybe a little smaller. What about just the set 0, 1, or the set AB? An interval. You think it's connected? How many people say yes? Yeah, you're right. It's connected. Let's do a proof. And as these proofs go, to show something connected, it's a lot easier to do it by contradiction. Why? Because if it's not connected, there exists a separation, and you can work with that. Okay? So, here we go. Proof. If not, then there exists a separation. I'll abbreviate separation. Let's say A and B. Okay? With, let's just put little a and big A. So here's the interval, little a and b. And here's a set. Whatever the set is, maybe the set, who knows? I don't know what's true about these sets A, but maybe big A is like, who knows? Maybe it can contain several different pieces. I don't know. And let's say B, the other set B, contains several different pieces. Okay. And by the way, this set A could contain this endpoint B. I don't mean to indicate that little b necessarily is contained in big B. So what's wrong with this picture? We're trying to get a contradiction. What's true? A closure does not intersect B. B closure does not intersect A, yes? So we got to find a contradiction here in this picture. Where would you say it'd be good to look, a good place to start? Yeah, some endpoints here, right? So let's do that. That's a great idea. So Rebecca said, let's look at an endpoint. How about this endpoint? Let's look at, how about the rightmost point of A, otherwise known as the supremum of A. Love that idea. I'm glad I thought of that. Okay, excellent. Yes, it is okay. Let's just see how to modify this proof if that happens. Okay, excellent thought. So let's let S be the supremum of A. Then, what do we know about the supremum? Well, it's got to be in a closure, isn't it? Because either it's in the set or it's a limit point. It's approached by the points in A. Yes? Mm-hmm. Oh, yes. Sorry, these are non-empty. Thank you. Yes. Sorry, so coming back here, the question was, shouldn't these be non-empty? And the answer is yes. Okay. And actually non-trivial. So it's non-empty, not the whole thing. So so by non-trivial, I mean can't be empty and can't be the whole thing. Otherwise, the other one would be empty. Okay. They're automatically separated in E. So if you just restrict yourself to E, the fact that they're both open means that they're also both closed, and therefore they're both clopen in E. And therefore, the closure of this set, of the set in E, is just itself. And so it will never intersect the other set. Okay, so this is all taking place in E in the relative sense. Okay, so if they're both open, they're both closed, and they're both clopen in the set. Okay, it'll take a little thought. For the most part, we're not using these definitions. I'm telling you this for culture because you'll encounter this in topology if you take topology. in the real line, we usually use that definition because we think of this set as being part of the real line rather than existing in and of itself. Okay, so back to this proof. If S is a supremum, let S be in, then S is got to be in a closure, right? Because either it's in the set, or if it's not, then it's not anything smaller must be not an upper bound, so there has to be a point very close to the supremum. In your book, this is 2.28, and we did show this in class as well. So if S is in a bar, then what this means is this last point is actually in a closure. Therefore, it's not what? In B. Okay, so if S is not in B, then where is it? Then it must be in A. Dot. Oh. But if it's in A, we're still trying to get a contradiction. What's the contradiction? If it's in A, then it's not in B closure. By definition of separated, using the other condition. So if it's not in B closure, what does that mean about this point, this red point? It has an interval around it that completely misses B. Oh. Then there exists an S minus epsilon and S plus epsilon, not in B, containing no points of B. Oh, but A and B are the whole set, right? So this interval must be where? In A. Hence, all in A. But why is that a contradiction? Because S is the supremum. But this contradicts S as supremum of A. Okay, let's answer Laura's question as to how you would modify this proof if, in fact, the endpoint were, if sup A was B. You would not get this contradiction anymore because there isn't anything beyond. And so this interval, well, it's still fine because there's nothing on to the right-hand side in the relative topology. So what could you do, Emil? Yeah, you could use the infimum of B. Okay. So fix this as appropriate if it's not the right-hand endpoint. Okay. Yeah, this probably could have just made this a lot easier by just looking at the infimum of B. Or I could have started with the set that doesn't contain B. Yeah, very good. Okay, that's a good place to stop. With the remaining 5 minutes or so, I'd love to get your feedback about this course and how you're doing and how I'm doing, etc. Thanks. Next time we're going to start talking about Chapter 3, which is sequences.